This video will focus on the ideal gas law, saying I can solve for pressure, volume, moles, or temperature using this law. So we already have a relationship for pressure and volume and temperature, but there is one more relationship, and that's with number of moles of gas. So it's called Avogadros principle. This is the guy who first discovered the mole and found out kind of how the mole worked. And it's actually because he was working with gases. And what he found was that the volume of the gas was directly proportional to the number of moles of gas. Meaning if he increased his amount of gas, the volume would change as long as pressure and temperature were being held constant. So they had a mathematical relationship that as volume went up, moles went up. The relationship of what we do with the moles then is kind of here on the bottom blue box. We know PV over T is a constant, and that if we change them, that they're, proportional to one another. But that constant, eventually they discovered it, they calculated it to be a number they call R, and R times N was the same constant as PV equals as PV over T. So essentially, PV over T equals N times some constant always. And that's how N kind of joined the club. If you look at that then, we can expand our combined gas law just a little to now include moles in it. If we look at the relationship with N here, we can pull N over, divide it down, and that means the initial condition, PV over T, can now be PV over Tn equals PV over Tn. And this is the basically final combined gas law that includes everything, including number of moles. So as moles go up, volume goes up, but that is now incorporated into the entire thing. If moles go up, we can also see how that affects pressure and temperature variables as well. The ideal gas law then is a way to relate pressure, volume, temperature, and moles of gas in any scenario in kind of like a snapshot. So it's like a one-off situation. So combined gas laws with PV over T equals PV over T are like a changing condition. If I have a pressure and change the pressure, how do the volume and temperature become affected? Ideal gas law, on the other hand, is a snapshot. If I know pressure, volume, and number of moles, I can predict temperature from that. Okay, so the equation's right up there. It's PV equals nRT. We often call it PIV-NERT. You can see that there's no ones and twos. It's just a one-off in terms of their relationships. So P is pressure, and it can be an ATM or KPA, and I'll tell you how you know which one. Volume has to be in liters, though. Temperature has to be in Kelvin, as it has been. N is number of moles, so it's your mole number, like 2.7 moles. That would go in for N. Okay, never mass. You get mass to moles and then plug it in. Anytime you take a situation with gases and take the pressure times the volume and divide it by the number of moles times the temperature, you get a number that we call R. And R is called the ideal gas law constant. And if you change the scenario, so like a new pressure, volume, temperature, mole relationship, you always end up calculating the same R. Okay? So R is essentially a constant, we call it, but it's just a constant of relationship. It allows these four variables to be mathematically related. We know they're proportional, but in terms of making their numeric values work out, you need R. Because if you just think about it label-wise, if you take like pressure in ATM times volume divided by moles and temperature, like nothing would cancel, right? So R is the proportional constant, it's called. It's called the ideal gas law proportional constant and allows these four things to be mathematically related. So biggest thing about R then is R is just a number, okay? It's just a number. It's the number 10 because that's how it relates. It's the number 7 because that's how it relates. Okay, it's just a number. On the bottom of the screen, you see what two R's are. Okay, these are the two R's we're most likely going to be using. So R of 0.08206 or R of 8.314. And essentially, how you choose which R to use is based on its label. So R is just a constant, it's just a number, but it's a relational constant. So essentially, it has a label to it that allows all of the other labels in PV equals nRT to cancel out. So that part right there of the R, that's just the label. That's just to make things cancel. So the label on 0.08206 is liters times ATM divided by mole times Kelvin. And the reason that is the label on it is so you can mathematically use this equation. So let's imagine I had a sample of gas like this, where I knew its pressure, I knew its volume, I knew its mole, but I wasn't aware of like what the temperature was of that gas based on this scenario. Well, I can use PV equals nRT then to solve for temperature. Okay, if we look at PV equals nRT and rearrange it to solve for T, that's PV over nR equals T. So that's what I'm going to be solving for. So now let's see what happens when we plug all our labels in. So if you just look at PV and N equaling T, here's what we would get, right? We have our values here, but if you look at the labels, the final answer would be an ATM times liter divided by mole, which is not temperature. That is not Kelvin. Now, if we add our R, our constant, what that's going to do is allow the labels to work. So mole times this, where mole is in the denominator, those are going to cancel. Liters are being divided by liters. ATM is being divided by ATM. Kelvin's on the bottom here of the bottom, so that's going to flip up as we rearrange, and you'll get your final answer to have just the label Kelvin. So what the gas law constant does is allow all the labels to work to be able to mathematically solve for one of the variables in the ideal gas law problems. Now, again, R is just a number. I'm not going to have you cancel labels. I want you to see how it works, but R is just a number. Now we have two R's. I'll show you in class, so there's a whole table of R's because R is just based on what labels you're trying to cancel. And if you look at R2Rs, the difference between R2Rs are the pressure. So the first R, 0.08206, you'll use if you're measuring your pressure in ATM so that they get canceled out. If, on the other hand, you're using pressure in kPa, you'd use 8.314 so that the kPa pressure label gets canceled out. Okay? So it's just a constant. Mathematically, one of the challenges of this unit then is how do I know to use combined gas law versus ideal gas law? And I often say it's a difference between a changing condition and a snapshot. Okay? So combined gas law is a changing condition. I have some initial and some final. That's going to be like a P1 V1 over T1 equals a P2 V2 over T2. Ideal gas law, on the other hand, is a snapshot. It's a single condition over one instance where I'm trying to calculate one of the variables. So look at the first problem up here. I see when the temperature is at this and the pressure is at this, and the question asks if the temperature changes, what's the new pressure? That is a combined gas law because I have an initial temperature, initial pressure, a new temperature with a new pressure. If you read the bottom one then, I have a temperature and a pressure and a number of moles, and I ask for the volume. That's the ideal gas law. That's a snapshot. I have 1 and 1 and 1 and 1. I'm just going to solve for the one I don't know. Essentially, I problem solve these all the same. I identify all of my labels, but then I plug them into different equations. So for my first problem up there, I have an initial temperature, initial pressure, and then change my variables. So that is going to be one of the combined gas laws, where it's pressure over temperature equals some unknown pressure over temperature. So this is just a cross multiply and divide scenario to solve for my pressure 2, which will be an ATM. On the other hand, for the bottom one again, there's no changing variable, so it's the ideal gas law. It's just a snapshot where then we plug into the equation P times the unknown V is going to equal my N times my R, and I'm going to choose the R based on ATM. So I'm going to choose that 0.08206, and then I'm going to multiply that by the T. So PV equals nRT, PivNert. Now this one's a cross multiply and divide. This one's a rearrange and solve for the unknown. So I'd go 1.41 times 0.08206 times 139.4, divide 3.13 over, and that would solve for my volume then. Since my R has liters, my volume then will be in liters because that's how the labels work. So that's your overview of the ideal gas law calculations. Go ahead and do the quiz and have a nice night.